In this video we're going to look at how principal component analysis can be used to noise reduce a dataset. Before processing these data, I'll just explain a little bit about the dataset itself. We have three different narrow scan regions, and each one of these has been collected using a 2D detector such that the non-energy dispersive direction can be accumulated into individual spectra. So effectively we have separated what would normally be a single measurement of three different regions into a set of 20 measurements, one per region. So we have 60 spectra in total. Each silicon 2P spectrum has been scanned in the sense that the retard ratio has been adjusted and then signal collected and then stepped over a range in order to produce a variation of signal as a function of kinetic energy. The less conventional nature of these data is that for each energy for which signal is acquired, data is split into a set of channels. One of these channels represents a different position on a 2D detector in the non-energy dispersive direction. I'll use these data to illustrate some display features as well as the principal component analysis. There are options on the options menu that let you save a tile format. So this is the display that has now been saved in a temporary form for this particular view. And I can adjust the display in terms of number of tiles using the page tile format. I'm going to select 2 and I'm going to say I want 2 columns, and when I press OK, the page of tiles then changes. I've got 1 tile, but I have the possibility of displaying 2. So the next thing I'm going to do is display a second tile, and again using the options menu there's add tile. So this has taken a copy of the selected tile and reproduced it in this empty space. So the objective of doing this is that I would like to display in this second tile an image rather than data, and this is a new feature. And if I select on the geometry property page the option for annotation tables only, that is to say I could just display annotation tables from the data, in fact these silicon 2P data, in this tile. However, if I turn off the annotation, then rather than displaying tables or a blank tile, I've got an image that is in CasaXPS.def directory, which I can then display in this tile. So with the aid of this image I can now explain better how this dataset was collected. If I change this to a 3D plot and then reverse the plot, I can then see how the 2D detector has been used to collect these data. This is the energy dispersive direction, and in this direction data are collected using different slices of a 2D detector in the non-dispersive direction. And you can see how there's a variation of signal as a function of this non-dispersive direction, and this is because these data have been collected using angle resolved type lens functions. Making use of these lens functions allows different electrons from different angles with respect to the sample surface to arrive at the entrance to the HSA, and then to traverse the HSA and arrive at a unique point on the detector. So we have 2 paths here. The first one is from a shallow angle, so this is favoring the surface, and if this was a thin film of silicon oxide on silicon, then we would expect electrons leaving in this direction to favor the oxide. So they've arrived at a detector here, so this represents one of the detector slices at the extreme end. This is one here. So we end up with a spectrum that has more oxide peak than an elemental peak. This is the elemental, this is the oxide. If on the other hand the electrons are gathered from a more perpendicular direction to the sample surface, then the sampling depth allows us to see more of the silicon. So this blue path represents a point at which the electrons from a normal direction arrive at the entrance slit to the HSA, and then the mechanisms of the HSA transfer these electrons to the opposite side of the 2D detector, and so we end up with a spectrum that can be collected if we separate the non-dispersive data channels, showing a greater amount of silicon and less oxide. The advantage of using a lens system that can separate signal in this way is that we get to see how the sample varies as a function of depth, and this is reflected in the relative proportions of the oxide and the elemental silicon. The disadvantage is that each individual spectrum is recorded with a lower count rate, and hence the signal to noise is not as good as if we summed all of the information. If we sum the spectra, we lose the depth information. So what we'll do now is use principal component analysis to derive spectra from these data that have enhanced signal compared to noise. We'll now return to the display state as when this video began, and I saved the format using this options menu, the save tile format, and I can restore that tile format by using the menu option restore tile format or Control X. So I've now returned the display, but before I continue I'm just going to bring up the tile display parameters and click OK. And the idea of doing that is that the display that I'm looking at now becomes the default display. So if I wanted to select another set of spectra and use one of these insert buttons, then the format of tiles and the other display parameters such as the fonts and the grid pattern, they've all been preserved by that action of bringing up the tile display parameters dialog window. The PCA options for Spectra are on the spectrum processing dialog window on the PCA property page. The noise reduction in these silicon 2P spectra can be achieved using three options on the PCA property page. We have number of factors, predict using factors, and generate factors. The first step is to work out how many abstract factors are significant to these data. We can do this using the generate factors. And since we've got 20 spectra, we could specify the number of factors we wish to calculate as 20. And if I press, having overlaid the spectra in the active tile, the generate factors button, the spectra are transformed by an iterative singular valued decomposition that allows a limited number of abstract factors to be calculated by a PCA. Now the number of abstract factors that have actually been calculated in this case is indicated by the factors equals 5. So rather than calculating all 20, only 5 of these abstract factors were calculated, and that is because the fifth abstract factor has variation that is consistent with Poisson noise. So the algorithm terminated after calculating 5 abstract factors. We can calculate all 20 if we use a button here that says correlate about the origin, but this is just a button that indicates to this calculation here that all 20 should be used. So I've returned the spectra to the original state using the reset processing, and then I'll say generate factors, and this time you can see that it has indicated all 20 have been calculated, and that's a consequence of having this selection here. We can now look at these abstract factors and work out which ones we believe are necessary for reproducing these data. So let's change the display so we can look at 4 at a time, and we'll go to the top of the display. And you can see this is the first abstract factor. This corresponds to the top FAMAS block here, and it looks very much like this average spectrum. It's not quite the average spectrum, but it looks very close to it. And then we have a sequence of abstract factors that have various shape information that look consistent with the peaks that you might find in the data. And then the fourth one, we've got a very subtle variation, and the fifth one, this is the one that was determined to look more like Poisson noise. So wherever there was a peak, you see an increase in intensity, and in the background you see smaller variations, and this is consistent with what you'd expect for pulse counted data. And the other abstract factors are continuing to show similar sorts of limited variation. So as we scan through all of these, you can see that they are very much in the image of noise from Poisson type data. So we'll go here with 4 abstract factors representing the information in this data set. Let me overlay these again in a tile so I can reset them. So I've now reset all the data back to the original state, and if I've decided I've got 4 abstract factors with information, I enter in the factors field a value of 4, and then I use predict using factors, and this will apply to the active tile. So all of these data overlaid in the active tile are going to be processed. A PCA will be performed calculating 4 abstract factors, and in this case the predict using abstract factors will always calculate the number of abstract factors that are specified in the factors field. And when I press predict using factors, I've used 4 abstract factors, and now these spectra are transformed so that noise has been removed to some degree. And you can see that the success of removing the noise varies across this data set, and one of the reasons for that is that the range of intensities varies across the data set, and those oxide peaks had very little contribution to the overall variation, and so they were represented to a lesser extent compared to these more intense peaks. But nevertheless, you can see the variation if you use the residual. One of the byproducts of this calculation is that the background has retained the value before the calculation, and the spectrum that you're looking at is the noise enhanced spectrum, and the difference between the background and the spectrum is the residual, and so you can get an indication of the type of error that would be incurred if you replace your spectrum by the noise enhanced data. So this is looking reasonably good. It looks like Poisson type statistics, especially given that we have a multiple channel detector in the energy dispersive direction, so you tend to find that the residual is less than 1 and about 0.886, something like that. So if I look at all of these data, you can now see that there's one about unity, 0.9, 0.96. We go down, you can see that for data with significant signal, the residual is close to unity, and as you go further down where the data had poorer signal to noise in the first place, you can see the residual isn't quite so good as the more intense peaks. The algorithm used to calculate abstract factors on the PCA property page is iterative singular value decomposition. This is described in a PDF on the CasaXPS website, and there's also a reference to a paper where the algorithm is used in the context of image processing. But essentially the algorithm calculates one abstract factor at a time. We can investigate how this algorithm works by looking at these spectra and treating them as vectors and constructing a covariance matrix. This can be done on the image processing dialog window, and the result is an image that is representative of the covariance of each one of these vectors, that is to say the dot product between vectors. If we've performed a principal component analysis, one of the properties of these vectors would be that they are orthogonal. So let's first of all calculate all 20 abstract factors, and when we construct the covariance matrix we end up with a diagonal image. This is because each and every one of these are mutually orthogonal. So when you take the dot product of any of these abstract factors with one another, the off-diagonal elements are 0 for orthogonal vectors. So you can see as I click here, we're looking at values 10 to the minus 12. Now if we go back and rather than using 20, we'll repeat the calculation and use 6 abstract factors rather than 20. So when I say generate, there's a similarity here in the in what you see. However, when we go to the covariance matrix calculation, rather than a fully diagonal matrix, what we have is the most significant abstract factors are mutually orthogonal to all vectors, but after 6 they are no longer fully orthogonal. So if I go to the color scale and click here, you can see that the dot product of any of the vectors lower down, so any of the 14 vectors that are not part of the 6 that have been calculated, potentially have large off-diagonal values for the covariance matrix, and this shows that they have not been fully diagonalized as a singular value decomposition.